Hello Pre-Calc Honors kids. We're back with part 2 of 11.3 day 1 and we're going to complete the note sheet, but there will be items that we skip because it's things that we're just not going to have time to cover this year. So we left off right here and you can see that I've added parentheses. For some reason the document uploaded, and it may have done that on your end as well, without the parentheses. These next two examples are really just emphasizing those properties of limits that we had in the first video, and you can go back and look at your note sheet and look at those properties. And just to recall that a limit, as the input value of gets arbitrarily close to a certain constant, what is the, let me back up on that. As the input value is approaching a certain value, what is the output value approaching? And these next two examples, I'm giving information. The limit as x approaches a of f of x equals -3, and the limit as x approaches a of g of x equals 5. We're going to find these limits. So again, go back to that property list from day 1, and what you're going to realize is that we can break up this limit if it's a sum, and I can even break this up more. This 2 can come out in front. Now, 2 times the limit as x approaches a of f of x. Well, we've learned that that equals -3. And in your properties, the limit as x approaches a of a constant value of 3 is just that constant. So we have -6 plus 3, and our limit value will equal -3. I would like you to make an attempt at B on your own. So pause the video. Okay, and so you can follow along with my work, again, using that properties table. Next, we're going to cover following limits graphically, numerically, and algebraically. And you'll find that I just took a clip from some notes from your book, and I'm going to find the limit as x approaches 1 of x cubed minus 1 all over x minus 1. So you could see this graphically. You can see this numerically by using a table. And you can see the algebraic approach. So if we look at it graphically, you see is we get pretty close to 1, and we're looking at that output. I really like numerically. I like looking at that table because it really emphasizes that left and right. This is considered that left hand. This is considered that left limit because the values are smaller than 1 and they get arbitrarily close to 1. And you can see the output looks like it's approaching 3. And this is considered that right hand because values are larger and they're approaching 1 in this direction. And we can see it's approaching 3. And so at that point in time, I can comfortably say the limit's 3. I'm going to prove it algebraically. And you can see that I cannot plug 1 in because then I would end up with something called an indeterminate. I'd have 0 over 0, but I really don't want this. The numerator x cubed minus 1 is a difference of cubes, so you see me factoring that because we can only divide out things that are common factors and they need to be in factored form. So this divides to 1. It gives me a new function. We talked about that in that prior video. They look really similar, like the graphs are almost identical. Now we can substitute in, and we've shown the limit is 3. I am going to skip the next section. I'm going to skip this section because we are low on time due to the circumstances. But I know as a calculus teacher, this is something that will be covered at the start of your calculus class. So it's okay that we skip that. If you'd like to explore it on your own, please feel free to. I want to go here and do steps for the limits algebraically, because that's going to be the next thing we cover. So these are some really basic steps. The first thing you should always do is try to substitute in that x value or that input value, the value that it's approaching. If you get a constant, then you're done. You have your limit. But if not, then we need to do a little bit more work. We may need to do some, I showed you, we found that new function that's almost identical, and that's what I mean by rewrite the statement to get something I can manipulate a little bit, and then try to substitute again and see if I can get that constant. So here are some two really, really basic examples. And the first step is substitute. Now I cannot drop off this limit as x approaches 3 until I've substituted the value of x in and it works. In calculus, we need to keep writing that limit down. However, I get to substitute in and recognize the fact that I'm going to get an answer. Okay. I'd like you to pause and try B. You should recognize in B that you can go ahead and substitute in, and you will get negative 28. So we only needed to do step 1. Examples C and D are examples that we need to skip since we skipped that above information. This is prior material that I'll quickly talk about. We've already discussed this year what happens is a graph of a function, and in both of these I have rational functions, approaches a vertical asymptote. We've also done horizontal asymptotes. So we know that as a graph of a rational function approaches a vertical asymptote. And I want to be specific. A rational function, a polynomial divided by a polynomial, the graph can go to infinity or negative infinity. So this is just something you might want to review. This is newer material, dealing with piecewise functions and limits. I am confident that you haven't been super exposed to graphing a piecewise function. So at this point in time, I don't want you finding the limits. I'd like you to make an attempt, pause the video, and graph f of x. I started graphing this. I graphed 3 minus x for x is less than 2. That is the only time that linear function is defined. But what's interesting is I had to start with that open circle because it does not say includes 2. However, in the next step, when x is 2, y is 1. So in this case, this hole, shall we say, gets plugged up. And then anytime the domain is greater than 2, I have x squared. So if I plug in 2, I get 4. Now, I'm going to have that as an open circle because I'm not including 2. Okay. And then I'm going to go ahead and just kind of do a rough sketch from here. Now I have a visual, and I should be able to do those limits. So the limit as x approaches 2 from the right. So we're not moving right. When I say from the right, we're saying numbers to the right of 2, so larger, and then moving towards 2. So I'm going to draw an orange arrow on how we're approaching that. And as we approach 2 from the right, y approaches 4. As we approach 2 from the left, I'm going to draw some green or teal green arrows. Left means to the left side of 2, not moving left, but moving towards 2. Sorry, my OneNote is not happy today. And so we're moving in this direction. And so I get 1. As learned in the previous video, if the limit from the left does not equal from the right, then the limit does not exist. We also now know that f of x cannot be continuous because the limit as x approaches 2 of f of x, we need to include the f of x, does not exist. I want to be clear, this notation, you cannot do that. Please pause the video, get the next piecewise function graphed, and answer the question. Okay, so you can now see my graph, my answers. Even though the limit from the left equals limit from the right, and the limit exists, this function is not continuous because the limit at x approaches 2 does not equal f of 2. One more example to go, and again, I'd like you to pause this video and do this on your own. And now you can see my end result. This is the end of the second part of 11.3 day 1. There will be one more video for 11.3 for you to watch, and it will be covering all algebraic limits. Have a great day.